So the electromagnetic spectrum, all these different wavelengths of light, you are most familiar with only a tiny little piece of it between 400 and 700 nanometers. That's the visual light. This light, when it goes into your eye, does several things. So some of the light triggers different cells in your eye. You have 4 different detectors in your eye. 3 of them are called cones, and 1 is called rods. The rods are broad spectrum. They actually don't pick up the red very well, but they pick up most of the other colors pretty much evenly, and they work at very low light conditions. But they pick everything up, and so that means that you don't see color with rods. You see black and white. If you get where it's really, really dim out and look around, you don't actually see any color. You just see black and white. And that's because you're only using the rods. The rods tend to be interconnected in such a way that they pick up light much more dimly or with lower illumination. But the rods also use a chemical that is used up in bright light. So that means when you first walk outside at night, you don't have that chemical called rhodopsin. You don't have enough of it, and so you cannot see very easily at night until you build up enough rhodopsin in your eye to actually see things. So that takes a while to start seeing outdoors at night. The cones, some of the cones see mainly the red end of the spectrum, okay, and then some of them see kind of the green and orange end of the spectrum. So those 2 overlap, and then you have some cones that see the blue and the violet. Because 2 of the cones tend to overlap, there's a common genetic defect in which you're missing one of them. You still see just fine, but you cannot differentiate between red and green colors. And so this is what we call red-green color blindness. It's much more common in men than women, but it is a type of color blindness. If you're missing one of the other rods, that limits your ability to see the blue and the violet or distinguish it. Very few people, when they're colorblind, actually see no color at all. It's not like they have no rod or no cones. But what's happening is that they're missing one or the other, or they're depleted, so they don't see very well in that color. But that's that very narrow range right there. Now, but you're missing all these other wavelengths of light. Now, clearly, there are things that give off radio waves that don't give off visual light. That, for example, TV stations, TV antennas, and radio antennas would do that. X-ray machines give off X-rays, but you don't give off visual light when they do that. There's nuclear radiation, nuclear things that can give off, certain kind of isotopes give off primarily gamma rays. And so, and then microwave ovens, the microwaves are actually invisible. And then likewise, infrared light and ultraviolet light you can't see. And so that's extra sort of things you can't see, but they're out there. And there are some things that give off primarily those things and not so much visual light. So astronomers need ways of measuring all that. So a telescope is your kind of go-to instrument, and the early telescopes were purely visual instruments. But modern telescopes are actually using things other than visual light to measure. We X-ray telescopes and gamma ray telescopes. One big problem that any kind of measurement makes from the surface of the Earth is we have to look through the Earth's atmosphere. The air molecules actually scatter light. So light from space will come into the atmosphere, and what happens is the blue light tends to scatter. So that means a person standing over here looking up would see blue sky from all the blue light scattered. But someone way over here would, looking low in the sky, that blue light being scattered to give this other person a blue sky means there's less blue in the spectrum. Well, remember, we got red, orange, yellow, green, blue, indigo, and violet. So if you get rid of that end of the spectrum, what happens is the person here looking low in the sky sees, first of all, everything looking dimmer because you've thrown away half the light. We call that atmospheric extinction. But it also looks redder. You've noticed the sun rising looks kind of reddish, or the sun setting. Well, the moon rising also looks reddish. Stars rising look reddish. Planets rising look reddish. Everything rising or setting looks more red than it does when it's high in the sky, because you are throwing away the short wavelength end of the spectrum. So what's left are the long wavelengths. Everything looks redder. So we have atmospheric reddening. Everything looks dimmer near the horizon than it does near the zenith. And that's because of atmospheric extinction. It all looks dimmer. The other problem you run into is that the air just blocks certain wavelengths altogether. X-rays, for example, people don't think about it because X-rays go right through you, but they have trouble going through air. Okay. Now, granted, it takes just a millimeter or so of lead to block it, but you can block X-rays with 10 or 20 feet of air. So you can get an X-ray, and the technician can leave the room, and just with a bunch of air between the technician and the X-ray machine, they don't get X-rayed. Because the air doesn't travel through the air. X-rays don't travel through the air all that well. Well, to look at X-rays in space, you have to look through 50 miles of air. So there's virtually no X-rays that make it to the ground. Most UV doesn't make it to the ground. The ozone in the upper atmosphere blocks the UV. If it were not there, we would receive a lethal dose of UV from the sun at Earth. Much of the infrared doesn't make it to the ground. Some does, but a lot of it doesn't. And so a lot of it's blocked by the atmosphere. Now, the thing is, it's blocked by the lowest levels of the atmosphere. So if you were to get higher in the atmosphere, you would get some of that infrared through to you. A lot of the radios make it right through, but really short wavelengths have trouble making it through, and really, really long wavelengths make it through. They have difficulty making it through the atmosphere. So the range of those wavelengths that make it through the atmosphere unimpeded or with minimal impedance, we call atmospheric windows. So those are the wavelengths that actually make it through. Where the atmosphere is opaque, that's not an atmospheric window. Okay. Now, the atmospheric window depends on how high up you are, because the infrared will actually make it almost to the ground. So what you would do is you'd situate your observatory as high up in the atmosphere as possible to minimize the effect of the atmosphere. So there's less turbulence, less distortion, less extinction, and more of the infrared makes it through you, and more of the microwaves. So this particular observatory here is actually in Hawaii, on top of the Mauna Kea volcano, which is an inactive volcano. And so these telescopes are some of the best ones in the world because the air is so clear right there. So this is where you'd build really big, high-performing instruments. And the other thing is that you have a lot of instruments here that are dedicated to infrared or microwaves, because the atmosphere, has less of an effect at high altitude. Radio waves. Radio telescopes can be situated pretty much anywhere because most of the radio waves make it all the way through the atmosphere. Problem is, you're still dealing with the atmosphere, so some radio waves are still an issue. The only way you get to where the atmosphere does not affect you is you have to get above the atmosphere. And there are, in fact, a number of space telescopes. On TV or in the news, you often hear about the space telescope, but the Hubble telescope is really just a space telescope. There are several other space telescopes. There's about a dozen space telescopes that are in operation, looking at different wavelengths of light. Some are infrared, some are X-rays, some are gamma rays, some are ultraviolet. So there's a variety of different instruments that are up there that are actually doing real good science. The Hubble telescope just happens to have one of the best publicities and PR offices, and it's one that people know about the most. It's a little bit bigger than some of the others and a little more capable, but the other telescopes are spectacular in and of their own right.